Hi, my name is Jim, and this is AC Circuits course, which is relatively challenging. And it's important that you refer to your text on this. It starts on chapter 13. So don't fall behind. And what's important in chapter 13 is you understand how a sine wave is made by a coil of wire that's being rotated inside of a magnetic field. Now, in AC circuits, since sine waves are pure signals, meaning they have no harmonics, they're of very important interest. So, what we're going to do is take a look at a sine wave, and instead of starting out in the electrical sense, is we'll start out with a clock. A pendulum of a clock traces a sine wave through time. Now, I've designated the sine wave, and this is kind of the way it looks, as right and left. So this is going to be the peak right deviation when the pendulum's on the right side, and the peak left deviation when the pendulum's on the left side. So if we start here at the far left, our beginning point would be here. The pendulum at this point in time instantaneously is stopped, and the slope of this point is 0. So if we drew a tangential line through this point, we would see that m, as in rise over run, is equal to 0, and then it starts to swing toward the center. When it's exactly in the center of the clock would be this point, and that's when the velocity of the pendulum is the highest. The rate of change of distance and time is the highest, and then eventually it ends up over on the right side where it comes to a stop again. That would be this point. Again, the velocity would be 0, and the slope of a tangent line drawn through that would be 0, and then it'll start to return to the left, and the cycle would repeat itself. Now, if we just took a pendulum and moved it over here and let it go, it would trace a sine wave, except there's friction and windage, and that's going to slow down the pendulum, and eventually the sine wave's amplitude, the size of this, would get smaller and smaller and smaller until it's stopped. So what's not shown in here is the tick, and that's potential energy stored in the spring, which gives the pendulum a little push at the right time, which overcomes the friction and windage. So somewhere in here the little tick would manifest itself as a little bump in the sine wave, but we're not going to be concerned with that now. So a simple clock traces out a sine wave. Now, also going to be talking about periodic signals, and what periodic means is they repeat themselves every certain time period, and that certain time period is called the period, and the equation for that is T, and this is a capital T, equals 1 divided by the frequency. So it's a direct relationship. As you can see, if we solve for f, it's going to be equal to 1 over the period. So this is a rectangular waveform. It's kind of like a square wave, 50% duty cycle, that repeats itself every period. So it would be a periodic signal. This is a sine wave that repeats itself, periodic signal. And finally, a noise signal, like if we're tuning between stations on an FM radio, is non-periodic or aperiodic. So let's take a look at the equation for a sine wave, and this starts out in the textbooks and math books as a or x equal a sine of the angle. And in our case in electronics, we're just going to substitute our terms into that, and then we're going to have to expand this a little bit. So instead of x, we're voltage with respect to time. So this is finding the instantaneous voltage at any point in time. A here, meaning the amplitude, would be voltage peak, sine of some angle. So if we take for an example a sine wave which is 10 volts in the positive direction and 10 volts in the negative direction, and say what's the instantaneous voltage at 30 degrees, we have our equation would be V of t equals 10 volts, the peak, sine of 30 degrees, and that would come out to be 5 volts. So if we expand this here, we would see the exact equation here with all the terms in place properly. So the sine of 30 degrees is 0.5. Now, it's incredibly important that your calculator be in degree mode here and later in radian mode. If you get it wrong, your answer is not close, it's really far off. So you have to be careful of that, and I'll try to remind you as we work through the course. So hopefully you'll kind of see this point, and probably the only question is why do I want to know the instantaneous voltage, and we'll have to save that for a later time. So we need to introduce the concept of a radian, and the argument for the sine function has to be unitless. You can't say the sine of 3 volts or the sine of 2 amperes. So degrees is simply a number, and radians is simply a number. So sine function has to have a dimensionless argument that we pass to it. And for electronics, that's usually in radians. And that's not a problem, it's just a few more steps to do. So a radian, if we think about a piece of pie, spelled P-I-E by the way, not the Greek pi, is defined as where the radius and the arc length are equal. And if we were to measure that, we'd find out it equals 57.296 degrees. So that would be 1 rad, and then the question now becomes is how many radians make up the whole pie? How many pieces of this can we fit in a pie? Make it blackberry pie, like blackberries. So what we find out is that the number of radians would be 360 degrees per unit circle, and where this 360 degrees comes from is that is 1 complete cycle. So it kind of makes sense. Divided by 57.296, and what we get out of that would be 6.28 radians. So we're about 6 1/4 pieces of radian pi in 1 complete pie. Okay, 6.28. So if we kind of look at it this way, 6 1/4 pieces of pie, we can feed 6 adults and 1 child. And the reason I'm going through this is that it is incredibly important that you be familiar with radians in respect of what they are and how to deal with them. So if we carried out here, what we would have would be 2 pi radians per unit circle. Okay, so 6.28 is 2 pi, except if you use the pi symbol on a calculator, it contains more significant digits than 6.28. Okay, what we need in our equation now is to substitute radians for degrees. Now the calculator must be in radian mode to do that. So you should have a mode button and select radians to do that. Now the equation, when we end up with this using radians, and now we're getting down into the meat of this thing, is the voltage with respect to time is equal to the peak voltage times the sine of 2 pi f. Now this is the total number of radians in the interest of what we're doing. So down here we'll see a little bit later that for 1,000 hertz, that's cycle per second, sine wave that would be 6,280 something. Then we're going to multiply it by t in seconds, and this is when you want the voltage. Okay, so total number of radians that we're interested in times t. And if we work out the units on this, we'd see that f is in cycles per second. That would be a cycle. How many cycles per second times the time, which is in seconds. So what we end up with is radian for an argument for the sine wave. So the the argument has to be dimensionless, and the units will tell you whether that in fact is correct or not. Okay, so let's take an example here, and what we want to do in this case is find V of t when t equals 62.5 microseconds. Now, what you need to be very familiar with is what microseconds means, and that's 10 raised to the negative 6 power, or on a calculator it's going to be inner exponent negative 6. So you have to be very comfortable with this of your units. It's also very important to have your calculators in engineering technology. You don't have to shift the decimal point on paper or in your mind. It's always going to come up as a power of 3, which means you're less likely to make a mistake. So we're going to let the voltage peak be 10 volts, and we're going to let the frequency be 1000 hertz, and 1000 hertz is equal to 1000 cycles per second. 1000 of these per second, and this used to be the term, but because of abuse the industry made it hertz. Engineers and technicians would say, what's the frequency? 1000 cycles. What? Per second, per minute, per hour? So hertz has the per second built into it, and then we would correctly specify that as 1 kilohertz, where that would be a lowercase k, capital H, lowercase z. So if we write our equation here, and it would probably be a good thing to follow along with your calculators, is V of t equals 10 times the sine of, and get this in parentheses, 2 times pi times 1000, or this could also be 1 inner exponent 3 times the time, and this has to be in seconds, so I entered 62.5 e to the negative 6. So going a little bit further here and just multiplying these two together is what I get as V of t equals 10 sine of 6283, and then taking the time, which I still have to multiply that, and I'm doing this step by step, hopefully so it'll become clearer. I hate textbooks where it starts out telling you something and then it'll say which gives something else, and there's 25 steps in between. So I'm going to try to do this one piece at a time so it's not confusing. All we have to do now is multiply these two together, and then we'll be in position to take the sine of it and find out what our voltage will be at 62.5 microseconds. Okay, so if we proceed here and we multiply the total radians by the time, as we end up with 393 e to the negative 3 as the argument of the sine wave. And then I've written that also in decimal form just to do it. And if we take the sine of this, surprisingly, for the values I picked, it comes out to be very close to the same number, 0.382. Multiplying that by 10 volts means that the voltage at our time is going to be 3.83 volts. So if we go back here a little bit, and if I have a sine wave here, this would be 10 volts, 62.5 microseconds. That guy right there would be 3.83 volts. So that's the thought, is a projection off the sine wave over onto the left axis, which is the voltage axis. Okay, so this kind of problem here is the core of what you kind of need to know. And if you walk away understanding this, you know, right now, you're in good shape. Alright, let's see if we can make a little sense of it here. So this is the same problem. I'm just going to explain it in a different way, which I hope will be a little bit more helpful. T, again, is 62.5 microseconds, and the period of the sine wave, again, is 1 millisecond. And if we take that millisecond, and this is what I do, and it's a good idea to do this, especially on a test, instead of punching numbers in a calculator, is this will tell you if your answer is reasonable. So my total period here is 1 millisecond, so I'm going to put at the end of the sine wave 1 millisecond, which is also equal to 1,000 microseconds. So if this is 1,000 microseconds, the 180 degree point is 500 microseconds, and the 90 degree point is 250 microseconds, and 62.5 is going to be sitting somewhere in here. So it seems to me that looking at these numbers is that 3.83 volts is a reasonable answer. Now if you make a mistake on a calculator and you end up with a negative voltage or something that's 8 volts or something like that, 62.5 microseconds relative to the peak at 250 microseconds doesn't make sense for 8 volts. So you did something wrong. So it's always a good idea, I think, to decompose the sine wave to the critical times. Okay, let's go on. How many degrees does 62.5 microseconds represent, assuming the frequency is 1 kilohertz? So we can do that in a simple ratio. Degrees would equal the 62.5 microseconds divided by the total period of the sine wave, which is 1,000 microseconds, right there, times 360 degrees. Now what's important to note is the units of microseconds divide out. They divide to 1. We're multiplying by 360, and we end up with an answer which is in degrees, 22.5 degrees. Now for a safety check, 10 times the sine of 22.5 degrees, calculator in degree mode, comes out to be the same 3.823 volts. And that's a little guy right there. So that kind of makes sense if we actually take our values that we derive from using radian measure and convert it back into degrees and do a double check on it. It comes out to be the same, and it has to. Okay, same problem, except now we're going to let the time equal 600 microseconds. And here's our equation again. V of t equals Vp sine of 2 pi ft. And I'm going to populate that. 2 pi times 1,000 times 600 microseconds. And this time, this is going to come out in the quadrant 3 as a negative 5.88 volts. So if we did the same thing with the sine wave and labeled the times that we're interested in, there's our 1,000 microseconds for the period of 1 kilohertz, 500 microseconds again. The negative peak is going to be at 750 microseconds, and for 600 microseconds would be somewhere in here. Any negative 5.88 voltage makes sense. If I would have got a positive voltage, not so good. Okay, so this is always kind of a good thing to do, instead of just blindly entering numbers into a calculator where if you miss a digit or switch 2 around, some bad things can happen. Now we're going to add in offsets, and this is going to add a bit to the complexity. And an offset means that there's going to be, the sine wave is going to be offset to the right or to the left. Okay, so if our offset is subtracting, we move to the right, and if it's adding, we move to the left. Now let's just take a look at an offset which is subtracted, and what we're going to use for an example is a cell tower, and there's a cell phone. Well, there's 2 signals that this cell phone is receiving. One is directly from the cell tower, which is called LOS, line of sight, and the other signal is bouncing off a building and arrives at the cell phone also. Now the deal is that the signal bouncing off the building is taking a longer path, so it arrives later than the direct signal, the line of sight signal, has a further distance to travel. So if we were to look at that, and this is included on your in a PDF in the folder here. And let me see if I can move this in and actually focus on this a little bit better. Excuse the professionalism of this, but there we go. Okay. What we see here is a reference signal in green going up to 10 volts. And at 400 microseconds, we get a voltage here of 9.11 volts. Now the signal that's arriving later, this is the later part, right here, between here and here. We have to basically shift it to the right by 30 degrees, and the question then becomes, how do we do that? Okay, so I'm letting these both be the same amplitude. In the real world, the reflected signal could be less than or greater than the actual line of sight signal. So let me back this up again, and we'll continue. Rotate, there we go. So for the offset, and this is a reference signal, we're talking about 5.87 volts, and you can see that the math is exactly the same as what we did before, letting the time be equal to 400 microseconds. Now we got to deal with the 30-degree offset. Okay, so what we end up with, the argument in here is radians, and the offset is expressed in degrees. So we're going to have to convert degrees to radians. Not hard to do. So for 30 degrees, the offset in radians would be 30 times 1 radian divided by 57.29 degrees. Now remember that 1 rad has 57.29 degrees in it. More importantly is to notice that the units cancel out, giving us radians. Working that through, we get 0.523 radians. Now, if you don't like to remember 57.29 degrees, what your textbook suggests is that to convert to radians, you would be multiplying, in this case, 30 degrees by pi divided by 180. And this actually is a more precise answer because your calculator is going to carry pi out to many digits. And likewise, if you wanted to find degrees given radians, you would multiply the radians by 180 degrees divided by pi. So I don't care which method you use. I kind of like this because I need to keep that number fresh in my mind, 57.29. This will give you a better answer, but you have to know how to do this. And remember, your units will tell you if you get it wrong. So anyway, what we have now, continuing this, is I've taken the 2 pi 1000 times 400 microseconds and multiplied all that together, and sitting in the sign argument is 2.513 radians. So that's this part, and then since this is arriving late, I'm going to subtract the radian measure which associates with 30 degrees, minus 0.523, and then adding these, algebraically adding them, actually subtracting this from this, we end up with the argument for the sine wave is 1.99 rads. And then V of t would equal the sine of that, which would be 9.13 volts. Okay? So for a little refresher here, if you have an offset, you have to convert it into radians, and after you get the big guy here, that is when you do your addition or subtraction of the offset. Let's see here, I guess it looks good. Okay, let's work another problem here, and now we're going to add 30 degrees, and let me kind of push this up a little bit again in this very expensive production environment that I'm working in. And when we add 30 degrees, is what we see is that we're actually starting out here. So when we add it, we're shifting to the left. And we want to find this also at 400 microseconds, and I've circled on these where those points are. And this, by the way, is the cursor, and this is in multisim. It kind of helps me visualize this, and this is very hard to draw accurately with the marker. So, and it also displays the voltages down at the bottom. I've just texted this so we can see what it looks like. Now, since this is the same problem, and the only thing that's different is we're adding 30 degrees, is we can use the same numbers as we did before. So let me pull this out a little bit. There we go. Tilt him down. So from the previous problem, we had our 2 pi ft sitting here. Now we're going to add in our offset. 30 degrees, convert into radians, and that'll give us a total of 3.03 radians, which gives us 1.05 volts. Now, this is telling us it's 983 millivolts, and I'm okay with the difference in this. And the reason is because of significant digits. Plus, I put the cursor at this point. Could have been off a little bit. I had to drag that guy. So I'm not concerned about the closeness or the difference between these two. What's good enough is good enough. Okay? So in the 5.83 at 400 microseconds is going to be exactly the same as what it was before. There's no reason for it to change. This is our reference signal in green. So here it's showing us 5.82, but you know, whatever. So the green is just reference, and then the red is showing this offset of a lagging signal coming in later. And the green is a reference, and the red is showing us a offset of a signal coming in earlier. Now there's reasons this can happen. I used the line of sight versus reflected before, and I'm not going to make a correlation at this time for this type of problem. So, hopefully once again you've seen two examples, one leading and one lagging. This is leading, and know how to combine the offset into the argument of the sine wave to give you the instantaneous voltage. Okay, let's take another example that isn't so clean. We're going to let F equal 150 kilohertz, V peak equals 2 volts, and the first thing I want to do is find out what the period is of 150 kilohertz. And the reason is, I want to put that down on my diagram so I know my answers are kind of close. So they need to make sense. So in finding the period, I see a repeating decimal here, 6.66 microseconds. And what I want to do then, for this example, would be find the voltage at 4.5 microseconds. So, what I know is that the whole period is 6.67 microseconds. The half period is 3.3 repeat microseconds. And the 270 degree point is 5 microseconds. So, and by the way, to get this, all you do is multiply this guy by 0.75. And if I wanted this here, 90 degrees, it would be this multiplied by 0.25. So 4.5 microseconds is going to be somewhere around here. And if I work the math out, here I've got the frequency, 100E3. I could have entered that as 150 followed by 3 zeros, but I entered exponent to more in better fashion. And this is a T again, 4.5 e to the negative 6, so that's in microseconds. And the voltage comes out to be negative 1.78, and that kind of makes sense here. Negative 1.78 looks right on my sketch of the sine wave. Okay, finally, and we can't do this right now because you haven't been exposed to phasors and so forth, but What about finding the voltage at a given point in time? And that has a lot of useful applications also. So we want to find T when V equals 7 volts, and our equation for a sine wave is V of T equals 10 sine of 2 pi 1000 hertz again, times time. And if I go down to 7 volts and draw a line across, is what I'm going to see is that I'm going to have two answers. So one of them is going to be in quadrant 1 and the other is going to be in quadrant 2. So what we need to do before we can solve this problem is to understand phasors, and that'll be coming up, well, next. I could also say something like find T when V is equal to 11 volts. Interesting issue. The peak voltage is 10 volts. So what's going to be the time at 11 volts? And the math will crash on you. You'll end up with a divide by zero or some other nonsense answer, which will be very obvious that you can't do this problem. It doesn't exist. So that's the introduction to sine waves, and now what we're going to do is, before we get into phasors, is look at the effective value, and that'll be in the next part. How much heat does this thing produce? It's a 10 volt signal. Sometimes it's 10 volts, sometimes it's 0, sometimes it's 3. You know, what's the equivalent of this? And what we end up doing is comparing this to a DC voltage and seeing what the value is up here that will produce the same amount of heat, say, in a toaster as if the toaster were run from 120 volts DC. So once we know that, then we can apply our sine waves in power situations without much difficulty at all. So this is probably, I would say, one of the most difficult concepts here, so you got to nail this, and then we'll move on from there. So anyway, thanks for watching.